Hello everyone and welcome to this presentation on the development of an automated rating system for a simulated oral proficiency interview. This work is being done by Second Language Technologies in collaboration with Midas Lab at IIIT Delhi. In this presentation, we will talk about the interview process and its scoring and how we are trying to automate the process of scoring. So what is SOPI? SOPI is SOPI or Simulated Oral Proficiency Interview is a performance-based speaking test that is commonly used as a surrogate for oral proficiency interview. It has 6 tasks which are aligned with CFR levels ranging from B1 to C1. To minimize cheating, SOPI has 8 equal set of forms. The SLTI SOPI is a double-blind rated test. A holistic rubric is used to rate the responses of this test. The rubric includes description about the task achievement, pronunciation, vocabulary and grammar, and fluency. Of the test 6 tasks that we have, 2 of them are of B1 level, which is rated from A2 to high B1 level. One of the tasks is of B2 level, which is scored from A2 to high B2 level, and the 2 remaining tasks are of C1 level, which is scored from A2 to C1 level. So how do we score these L2 English responses automatically? This is the pipeline that we are following right now. Once we have the recorded response, we send it to the automated speech recognition system, which transcribes it. The transcript as well as the audio file are sent to the cheating and sanity check module, and if any of the sanity checks failed, they are marked as unrated. If all of the sanity checks pass, we extract the NLP features as well as speech and prosody features through a feature extraction module. These features are passed on to the machine learning model, which predicts a score for us. Let's look into each module in a bit more detail. For automated speech recognition system, we use the Deep Speech 2 architecture with 4-gram language model. This system was trained on approximately 1000 hours of audio sample from public dataset and further fine-tuned on approximately 45 hours of transcribed non-native responses from our dataset using Ordino. The system achieved a word error rate of 20% on approximately 10 hours of unseen spoken responses. In the cheating and sanity check module, we have 5 checks. First, language detection, whether the person is speaking in English or not, and if not, the audio is not rated further. Second, reading of the internet, whether the parts of the response that a person has given are directly available in the internet or not, and if yes, those responses are marked as unrated. Third and fourth are something that we found in our dataset, which are repeating the question and reciting famous poems and prayers. So if a person repeats the question or recites a famous prayer or poem, we compare the transcript with these sources, and if it is found, then those responses are marked as unreadable. Finally, we have speaking improbable sentences. So someone who is trying to fool the system may speak sentences which are malformed and can fool the system. So what we do is we detect them earlier and remove the responses altogether and mark them as unreadable. In feature extraction module, we extract 5 types of features. First, fluency, which can be broken down into breakdown fluency and speed fluency. Breakdown fluency deals with different aspects of pauses, so things like filled pause rate, number of silences, etc. are part of this subcategory. Speed fluency deals with the speed of delivery, so things like speaking rate, articulation rate, etc. are part of this subcategory. Suprasegmental pronunciation can be broken down into stress-based features and interval-based features. Stress-based features capture occurrences and distances between consecutive stressed phonemes. So things like stress syllable rates, stress syllable distance, etc. These features are part of stress-based features. Interval-based features deal with features that are solely dependent on vocalic, consonantal, and syllabic regions in the speech. So vowel duration, consonant duration, and syllable duration, etc. are part of this category. We also extract response-based content features, which is nothing but TF-IDF vectors. The fourth category is grammar and vocabulary features. These features help assess the response across dimensions of accuracy and sophistication of language construct, and it can be broken down into lexical complexity and syntactic complexity. To study the impact of acoustic features on scoring, we included features like duration, pitch range, jitter, and shimmer in our feature set. In our experiments, we performed both classification and regression analysis. We observed that regression performed better than classification by about 4%. Hence, I'm presenting only regression results here. We compared various models like XGBoost, gradient boosting, random forest, SVM, and logistic regression and found that XGBoost performed much better than the other models. There is still, however, a gap between the performance of machine learning models and humans. This is something that can be attributed to errors in the automated speech recognition system, annotation disagreement between humans, and missing features like super segmental pronunciation, etc. More detailed results have been presented in the paper reference below. To understand which features were important to the model, we performed feature importance of XGBoost regressor across all prompts. What we observed was features like pitch, speaking rate, silence counts, audio energy, and number of different words in 50 word sequences were consistently found important across all prompts. Individual feature importance do not capture the impact of each feature category. Hence, we perform an ablation study where we remove each feature set one by one and notice percentage drop in quadratic kappa. On removing content features, prompt 1, 2, and 4 displayed a drop of 6% in quadratic kappa, while only 4% drop was noticed in prompt 3 and 6. Prompt 5 seems to be least impacted by content features. We believe this is because of prompt being more relatively open-ended and highly dependent on individual opinion. Dropping grammar and vocabulary features showed significant impact on quadratic kappa across all prompts. The drop percentage ranged between 7 to 13% for each prompt, thus confirming the impact of capturing grammar and grammar construct and vocabulary usage. More results can be found in the paper reference below. So what lies ahead? We have started working on the following things. Generation of feature-based feedback. So using the features extracted, we wish to provide feedback to a candidate why they were scored low or high and how they can improve their ratings. We would love your input on this. Second, multimodal deep learning approaches. So multimodal deep learning have proven to improve performance for automated speech scoring, and we have started working on it to improve our system. Third, improving automated speech recognition system. The current system can be improved for low score response, or accented speech, and handling of outer vocabulary words, and we are working towards it. Another thing we are working on is assessing specific aspects of oral proficiency, like content and coherence, which can act as a submodule to the current system. These are some of the references to the work that we have presented. Feel free to write to us if, in case you have any inputs, doubts, feedback on the work that we are doing, or if you wish to collaborate on any of the projects that have been discussed earlier. Thank you and have a nice day.